This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, welcome. I don't have any handouts for you today, so you're all cranking on assignment 1, which is intended to be very short, due Sunday night. The first real assignment went out Wednesday. That's due next Thursday evening, and at least until the midterm, I'm going to establish this Wednesday to next Thursday schedule with all the assignments, so there's some reliability as to how the workload ebbs and flows. When I left you last time, I was probably about 60% of the way through my L-search implementation. I'm trying to go from type-specific to general, or generic, but I'm trying to do that in the C language. So this is what I wrote last time. Void star L-search, and let's see if I can write the parameters out a little bit more neatly this time. Void star key, void star base, int n is the length of that array, int lm size is the size of the elements, and that's technically all the implementation of L-search needs in order to figure out where the boundaries are between neighboring elements. The fifth parameter is the one I want to focus on for the next 20 minutes. It has to have this as a prototype. I like the asterisk. You don't need it right there, but I like to keep it there. Oops, wrong way. And then I take 2 void stars. I don't need to provide parameter names here because I'm not implementing this function here. Okay. The basic algorithm for a linear search from front to back, that doesn't change. It's just the fact that we're trying to present an implementation that doesn't care about any specific one data type. So I want to do this for int I is equal to 0, I less than n, I plus plus. With each iteration, I want to manually compute the address of the ith element. I can certainly do that in terms of base, lm size is the quantum distance to move with each hop, and then I obviously tells me which element I'm interested in. Internally, I want to do this, void star lm address. This is the thing that's going to be compared against that key right there to figure out whether or not we have a match. This is equal to, numerically, base plus I times lm size. But we mentioned last time that this is strictly pointer arithmetic against a typeless pointer. Okay, now I'm sorry, the pointer has a data type. It's of type void star, so it doesn't know what it's pointing to. Several people have suggested or asked why they just didn't make it default to normal math when this is a void star. The specification of C just said I don't want to allow pointer arithmetic by default against a void star because there's a clear rule for what pointer arithmetic means when this is strongly typed. Okay, when it's weakly typed with a void star, very generic, I'm just pointing to anything and I have no idea what. You can't do this, the hack, and it really is a hack, but it's a well-known hack, is to sedate base into behaving like a character pointer just long enough to actually get a number out of this expression. Drug the base here, say you're pointing to characters. Do technically pointer arithmetic against the character pointer. Okay, this as an expression is an integer. It's technically multiplied by size of car, but that's 1. Okay, so this ends up being a car star that happens to point to a boundary between the I minus 1th and the ith element. I assign it to a void star. You do not have to cast the overall thing to a void star if you don't want to, because this is a more general pointer. It's willing to take on any pointer type. If after you do this, you use the comparison function written by the client that knows how to compare the things that reside at these addresses, pass in key, pass in lm address, and if that comes back with a match of 0, then go ahead and return, I want to return the pointer. So go ahead and return lm address. Okay, this ends the entire for loop, and if I get to the end and I have nothing to return, I'll just return null as a sentinel that nothing worked out. Okay? This replaces the double equals that sits in between two integers from the integer version we wrote in the middle of last lecture. Okay? Double equals between two strong types that are atomic, it knows how to do the comparison. In almost all cases, it just does a bitwise comparison and can come out with a -1 or a +1 or a 0. When you go generic on the C compiler, you have to say that I know how to compare the elements because I know, even though this is generic code, I know what type of array I'm searching. Okay? This code does not. So you have to pass in a little bit of a callback or a hook to tell the implementation how it should be comparing your elements. Okay? This is easy to understand. It's easy to just look at this and understand what's going on because you know what linear search is. That's not the hard part. The hard part is getting all the pointer math correct and the car start trick and actually aligning these things up properly and invoking the comparison function properly. Using this as a client is at least as difficult as understanding this code. If I want to go, just think in terms of the int domain, and I have the following. I have int array is equal to, this is a shorthand way of initializing an array. Int size is equal to, I'll just hard code it as 6. If I want to search for the number 7, okay, I actually have to do the following. Number is equal to 7. Okay, I have to set aside space for the key that I'm interested in because I have to pass the address of that thing as the very first element to the L-search call. Okay, does that make sense? You know that this is laid out as an array of length 6. The 7 resides there. I'm passing that and that width and 6 to the L-search routine. I'm hoping that it returns that right there. Okay? I want to find the place where the very first 7 in the array resides. Okay? Int star found is equal to, this is how I would call L-search. L-search ampersand of number. Array. No ampersand is needed. That there's an implicit ampersand because it's really ampersand of array of 0. Pass in 6. Pass in size of int. That at compile time evaluates to 4, at least in our world. Okay, and then I have to provide a comparison function. Okay, I want to write a comparison function that's dedicated to comparing integers. So I'm going to write that right now. Int compare. Now this would have to be defined as a function before I call this code right here, but I'm happy to implementing it afterwards. Okay. If it's the case that found equals null, then you're sad. Otherwise, you're happy. Okay. Does that make sense to people? Let me write the comparison function and so we can understand why it has to take the form that it is. int CMP, if it's going to actually compile and match this as a prototype, it absolutely has to take 2 void stars and return an integer. Okay, that is the class of function that's accepted as the 5th parameter right there. You may ask, well, can I just actually write a comparison function that takes 2 int stars and returns an int? Okay, and the answer is, you could, but you'd have to cast it to be this type right here. Turns out that since all pointers are the same size, you would pass them in as int stars and they would be absorbed as void stars. But it's just a much better thing to do is to actually write the comparison function to match that prototype exactly. Okay? The implementation of that is a little clunky, but it doesn't surprise you. It just has a lot of asterisks involved. Void star lem1, void star lem2. Just because some, let's write the 7 right here. This is the thing called number. On an arbitrary iteration, it may pass this in as the first argument to the comparison function. This right here is being invoked right there. Okay, it's going to pass in the address of that one isolated 7 right there every single time. Okay, the second parameter is going to get that and if it fails, then that, and if it fails, then that, et cetera, until it runs out of space. I have to return a -1 or a +1 or a 0, depending on whether they match or not. I also, because I'm writing this function specifically to make this call, this constrains the prototype to take 2 void stars, but I know that they're really int stars. So because I'm writing that code as a client, I can reinterpret the void stars to be what I know them really, I can reinterpret those void stars to be the int stars that they really are. So I will do this. Int star IP2, and I will just set it equal to a lem1 and a lem2. It turns out a pure C compiler, you do not need to do a cast there. It just understands that the cast is implicit. It has to do it. Okay. So I have these local variables, IP1 and IP2, that not only point to this and that right there, but they actually understand them to be 4-byte quantities to be interpreted as integers. Does that make sense? So all I have to do is return asterisk IP1 minus asterisk IP2. I'm relaxing a little bit on the return type. I'm letting 0 mean a match, and of course, if that difference is 0, then they're the same number. -1 and +1, I could constrain it to be that. I just want it to really be a negative number or a positive number to reflect the delta between the two. Okay? Does that make sense to people? So if you understand this, great. If you understand this, even better. I'm sure most of you understand this, even if it's the first time you've seen this type of code. Once we actually understand how all of this stuff works, you're going to be very, very happy. It's a little hard to get, it's a little hard to understand the very first time you see it, but you have to recognize that this is not exactly the most elegant way to support generics. It's just the best that C, with its specification that was more or less defined 35 years ago, can actually do. All the other languages you've ever heard of, they are all so much younger that they've learned from C's mistakes, and they have better solution for supporting generics. There are some pluses to this. It's very fast. You only use 1 copy of the code ever to do all of your L searching. Okay, the template approach, it's more type safe. You get more information at compile time, but you get code bloat because you get 1 instance of that L search algorithm for every single data type you ever search for. Okay, does that make sense? It's easy to get this right, easier to get this right, because you're not dealing with atomic types that are themselves pointers. We have integers right here. This gets a lot more complicated when you start dealing with the problem of L searching an array of C strings. Okay, so you're going to have an array of car stars, okay, and you're going to have to search for a particular car star, okay, to see whether or not you have a match or not. These are the int boards. I want to deal with this setup right here. I have, just draw some pictures first. Small array, 1, 2, 3, 4. And let's say I have an array of C strings, okay? Let's just assume that it's initialized this way. Okay, and I have an array of 5 little notes there. And I want to search the array using L search for an E flat. Okay. So here's my key that I'm searching for. It points to an E flat. I should emphasize that these are really character arrays that are null terminated. Okay, same thing with this. This right here is a character, character, character. This is a character array. That means that's a car star. Car star, car star, car star, car star, car star. The address of the array right there, the arrow I've just drawn in, is technically of type car star star. Make sense? How is L search going to absorb that? It's going to absorb it as a void star. The only way it's going to be able to compute that address and that address and that address as part of the linear search is because we're also going to communicate the size of a car star. So it can manually compute the addresses of all those boundaries. Okay? The comparison function that needs to be written in order to do this has to be willing to accept addresses of that type and that type right there. This is where things can get confusing because you can kind of drift back and say, well, everything's a pointer, so why does it matter that I pass in this as opposed to this? You're going to see when we write the comparison function that the number of hops from the tail of the arrow that's passed in really matters. Okay? If you're past this, if lsearch passes this type of pointer to your comparison function, then you really need to be you really are 2 hops away from the actual characters that are compared to one another. Does that make sense to people? You may ask, well, why doesn't the comparison function just pass these pointers in? The answer is lsearch has no idea that those things are really pointers. The only thing it knows is that they happen to be 4 bytes worth of information. Okay? Make sense? Let me declare this char star notes array is equal to, I'll write them as string constants, forget what they are, A flat, F sharp B, then G flat, and then an isolated D. I could talk about how these things are stored in a little bit. They're not in the heap. They're actually global variables that happen to be constant. It's like normal global variables, except they happen to be character arrays that reside up there. And these are replaced at load time with the base addresses of the capital A and the capital F and the capital D. Okay? Char star favorite note, as if I have a favorite note, it is E flat. Let me be very clear about this picture again. Actually, let me draw it again. Favorite note points to E flat. The actual array happens to be of length 5. It points to strings A flat, F sharp, B, G flat, and D. It's a cleaner picture. I want to search the array for my favorite note, E flat. The way you have to do this, char star star found. Now that enough is a headache, okay, to understand why it's a char star star as opposed to a char star. But we'll get to that in a second. This is the way you would call lsearch. I have to pass in the address of my favorite note. I don't have to, but I'm going to. I'll explain why in a second. Ampersand favorite note. I'm going to pass in notes. That's the name of the array. Think about the data type of notes. Notes is the ampersand of the 0th element. Since the 0th element is a char star, it's the base address of that capital A. Notes is synonymous with that value right there. So even though it's being absorbed by lsearch as a void star, because it was written generically, so that's the best it can do, we know that it's really a char star star. Okay? I have 5 of these notes. Pass in size of char star. Why char star as opposed to char star star? Because I'm interested in the actual width of these boxes so that lsearch can actually compute the boundaries between elements. And then finally, with capital S and capital C, I'm just contriving the name of some function called strcomp. There's 2 versions of strcomp, the one I'm writing and the one that's built into the C library, but the one that's in the C library doesn't have capital letters there. Okay? The reason I'm passing in the ampersand here is because I want the true data type of the key that's held by lsearch to really be of the same type as all the pointers that are computed manually as part of the lsearch implementation. Does that make sense to people? If I know that this and that and that and that and that are all really char star stars, it just makes life a little bit easier if you have some symmetry inside code that's otherwise very complicated to make sure that the key that's being compared against those 5 arrows is of the same data type. It doesn't have to be. Okay, I'll get to that in a second. But I'm writing it this way, so I pass in the ampersand of favorite note. So I get the ampersand of the tail of that arrow that points to E flat, 2 hops away from the capital E. I have to write the strcomp function. Even though lsearch returns a void star, it either returns a null, which we can check just like we did up there, or it returns one of these 5 arrows. Now, because E flat isn't in there, it's going to return null, but if I had asked for the index, or I'm sorry, the matching pointer to a G flat, it would return that. I know that there are really car stars in here. LSearch doesn't, but I do. So when I know it's returning this type of pointer, I know that it's truly of type pointer to car star or car star star. Okay? Make sense? Okay. Question right there?
The same as size of car star star?
Yeah, the question is the size of car star the same as size of car star star? The answer is yes, because all pointers, at least in our world, are the same byte, and they're always the same size on any given system and any given executable. You ask, I'm sure, just to be clear that they're both the same size, but you really do want this for readability purposes to be the true data type that's held inside the boxes of the array. Okay, I could, if I wanted to, put 17 stars there, okay, and it would still work. That doesn't mean the code is the best way we could write it. Okay, does that make sense? Questions? Yeah, right here.
Yeah, is it necessary to pass the address of where the locator is?
You don't have to. Right now, just for symmetry purposes, I'm making sure that the key and the addresses of all the elements in the array are of the same true type. I'll explain how we didn't have to bother with the ampersand right here. You only can get away with that if you really understand what's going on, and I'm just not assuming that that's the case in the first 15 minutes of the example. But after I write it the one way, I'll explain how we could have gotten rid of that ampersand. Okay, we get rid of these asterisks. Okay, so I have to write strcomp. I'm going to do it over on this board. Int capital S tr capital C MP takes 2 void stars. Gonna come up with better names this time. Void star VP2. The first one is always going to be that address right there because that's what I passed in, ampersand a favorite note. Okay, I know it's actually of type car star star. On an arbitrary iteration, it might pass in the address of that right there. Okay, makes sense? So now that I've caused the implementation of LSearch, that right there, to just momentarily jump back to my type safe code. The signature isn't type safe, but the code that's inside can become type safe if I actually cast things properly. So I'm going to go ahead and do this. You're going to love this. Car star S1 for string 1 is equal to asterisk car star star VP1. Asterisk car star star VP2. Now, why does that look the way it does? I'm casting VP1 and VP2 to be of the type that I know they really are. This type and that type right there. They're 2 hops away from bona fide characters. After I do that, I dereference them once so that this as a value and maybe this as a value are sitting in local variables called S1. I'm sorry, S1 and S2, okay? The reason I like that is because there is a built-in function as part of the CLib that is completely in tune with the fact that the notion of a string is supported as character arrays that happen to be null terminated, and that we pass around those strings by address of the first character, okay? This is the address of the capital E. This is the address of the capital G right there. What I can do is I can pass the buck to this built-in function with a lowercase s and a lowercase c, S1, S2. It takes 2 car stars, and it knows how to do the brute force comparison of characters one after another. As long as they match, it continues. If it ever finds 2 characters that don't match, then it knows that it can't return 0. It just returns the difference, the difference between the 2 ASCII values of the non-matching characters. Okay, that even applies if you hit a \0 in one before you hit a \0 in the other one. Okay, the delta is still what's returned. Okay, does that make sense to people? Okay, yep.
You passed it to 2 car stars.
Dereference.
Yeah, you dereference.
Why didn't I just cast it to be a car star?
Yeah,
That's actually the question that everybody asks right at this minute, the last 18 times I've taught the lecture. So this right here is saying, I'm recognizing the VP1 that's being passed to me is really 2 hops away from actual characters. So that's why the double star is really the right thing there. And then I want to get two values that are just one hop away from the real data, because that's what the built-in strcomp wants. Strcomp, just like my int compare function, it returns 0, -1, or +1. So it happens to return the value that I'm interested in. Okay? So you're questioning why double star here and then dereference once, when I might be able to just get rid of those two things and put char star? Is that what you're asking? Yeah. Okay. The problem is that asterisk in front of the open paren, as opposed to the other two asterisks on each line, that really is an instruction to hop forward once in memory and to do a dereference. If I, let me draw, actually this is fine. If I pass this as VP2, I say that you're not pointing to just, you're not pointing to a generic pointer, you're actually pointing to a char star. That's what the char double star cast does. And then when I dereference it once, I do that, okay? If I were to, given the way I've set up the call right there, if I were to do this, this would take this right here, and it would assume that the actual material right there are actual characters. Does that make sense?
Actually, I understand that. I just know what I'm saying. Asterisk right there. Like, they call it double star.
This right here? Well, that's actually the part that does the hop and goes from here to there, right there. You're just dereferencing a pointer. Okay? Does that make sense? Okay. Was another question flying up somewhere? Yeah?
Why do you need to cast it as a car double star then?
Well, what's the alternative?
Just like referencing the void pointer one?
Oh, you can't dereference. You could dereference. I see what you're saying. You actually could do that. That's going to confuse matters a little bit. But a void star you can't dereference because it doesn't know what it's pointing to. A void star knows it's pointing to a void star. Does that make sense to people? Okay. I actually want to bring it into the char star domain as quickly as possible, because then I really know sooner than later that I'm actually dealing with strings. Otherwise, I'm just leveraging off of my understanding of memory in a way that might not be clear to the person reading the code. Okay. Other questions? No questions? Okay. Now, somebody asked about this right here. My implementation of L-search up here, it's very careful to pass in key as the first of the two parameters to every call of comparison function. Does that make sense? Somebody asked, what happens if I forget the ampersand there? Well, my callback function still interprets whatever pointer is passed in as a char star star. So if rather than this being passed as the first argument to the comparison function every time, it passed this in, it would still do a dereference after it cast this to be a char star star. So that would mean momentarily it's pretending that the E and the B and the \0 and the mystery character that's right there, that actually represents a char star, and then it would pass that to strcomp. That would not be good, okay? Because it would jump to the E-flat mystery address in memory and just assume that there are really characters there. However, not that I like this for this example, but if you know what you're doing and you want to pass this in right here, you just don't want to deal with the overhead of a dereference when you know you don't need to, you could pass this in, and you could recognize that the first argument that's being passed in is actually one hop away from the characters, and the second one is actually two hop away from the characters. Okay? Well, I can say the way I wrote it first is the way it's typically written. Because of the symmetry they like, that I think coders just, I don't know if they like to see it. I think they're just in the habit of only dealing with comparison functions that really deal with the same incoming data type. Okay, and that's not the case if one's a char star for real and one's a char star star for real. Okay, so it is more common for you to put an ampersand right there and to do this just so that the first line and the second line kind of have the same structure. Okay. Okay. Now, for assignment 2, search certainly comes up. As opposed to all of these examples, you know that there's some sorted flavor to the arrays that you're searching there. If you haven't read assignment 2 yet, I'll try to be as generic as possible in my description. But you basically have the opportunity to do binary search as opposed to linear search for assignment 2. Okay. There's a built-in function called bsearch. It turns out that there's a built-in function called lsearch as well. It's not technically standard, but almost all compilers provide it, at least on Unix systems. I'm going to want you to use the generic bsearch algorithm. has more or less the same prototype as L-search right here. That's why I chose the prototype the way I did there. And it just does a generic binary search. You can implement it again yourself. If you already did, then don't go back and call bsearch that's built in. But I'd actually prefer you to use the built-in just so you learn how to use it. This is the prototype for that built-in. Void star is the return type. It's called bsearch for naturally binary search. It takes a void star called key. It takes a void star called base. It takes an int. I think it's called len for length. I actually like n better though. N always means size of an array. Int a lem size. And then it takes a comparison function that takes 2 void stars. The algorithm, in many ways, the pointer mechanics are exactly the same as they are up there. The only part that's different is that it kind of does this binary search to figure out what index to probe next. It assumes that the data is in sorted order. Now, I am going to say this, and you have to recognize that even though it doesn't sound very deep and insightful, it is. Okay? If you want to do the bsearch, use this function for assignment 2, and you want to do it as elegantly as possible. You have to recognize, kind of in sync with what I did over here when I erased the ampersand right here, you can pass in the address of anything you want to, okay? Provided the comparison function knows that the first argument is going to be the address of that something. Does that make sense to people? Okay? With the ampersand, I pass in a car star star. Without it, I pass in a car star. I could have constructed a record and put 4 pieces of information in there, passed in the ampersand of it, okay, and then just cast, I guess I erased it, no I didn't, I could have cast the address that comes in as the first argument to be the address of that type of struct. The reason I'm saying that is because you're going to want to do exactly that for assignment 2. You're going to need more than one piece of information to be available to the implementation of what you pass in right here, okay? As far as this is concerned, I've never said this in lecture before, but I'm glad I'm remembering right now. It has to truly be an actual function. cs106b and 106x, I don't want to say they're careless about it, but they're just not concerned about it at the time. They use the word function everywhere for any block of code that takes parameters. When I say function, I'm talking about this object-oriented less unit, which is just some block of code that gets called as a function that has no object or class declaration around it. Does that make sense? When I'm talking about the type of member functions or functions that are inside classes, I don't refer to them as functions. I refer to them as methods. Okay? The difference between a function and a method, they look very similar, except that methods actually have the address of the relevant object lying around as this invisible parameter, okay, via this invisible parameter called this. The type of function that gets passed right here has to be either a global function that has nothing to do with a class, or it has to be a method inside a class that's declared as static, which means that it does not have any this pointer being passed around on your behalf behind the scenes. Okay? I'll probably send it an email just about that one point, because if there are 2 or 3 problems that everybody has with assignment 2, one of them is related to this thing right here. Okay? Do you guys know about the this pointer from 106b and 106x? I think they actually used this even more in 106a when they talked about Java, and it seems to come up more there. But C++ methods, those member functions that are defined in classes, normally pass around the address of the receiving object via an invisible parameter called this. And if you need to, you don't very often have to, but if you need to, you can actually refer to the keyword this inside the implementation of any method, and it just evaluates to the address of the object that's being manipulated. Okay? That's what makes a method different than a regular function. Regular functions have nothing to do with objects, so there's no invisible this pointer being passed around. You have to pass one of those object-oriented less normal functions, or the name of one, as the 5th parameter to bsearch. Okay? Yep?
I'm just curious, so why is it that the comp function can be with or without the asterisk behind before it?
This right here? because these parentheses are here, it's clear syntactically that it has to be a function pointer. And until about 4 years ago, the asterisk inside was always required. Okay, and now it's just not, because just the lexers and the parsers know how to just decide that this is a function pointer type. Okay, I like the pointer there for various reasons, just because that's how I programmed that's how I used them for the first 17 years I coded in C, and then someone went and changed it on me, and I'm like, I don't care, I want to use it the old way. Okay, that's a very C way of looking at it too. Okay, there's nothing modern about C, so you shouldn't adopt any of its modernisms. Okay, any other questions at all? Okay, there are a billion little generic algorithms I could write, but I don't want to focus on these. You now have all the material I think you need to really make progress this weekend on assignment 2 if you want to. Okay, assignment 2 is definitely a jump up from assignment 1. Assignment 1 is intended to be all about Unix and just whenever you had time to get to it, just to learn the Unix that's necessary and then code up 20 lines of code to get RSG running. This is the one that really has some real C-isms that are required for the first half of the program. The second half where you do the search, that's very C++-ish. Okay, queues and stacks and all that kind of stuff, you've seen that before. Okay. What I want to do now is I want to transition from generic algorithms to generic data structures. And you probably have more practice with generics and templates in C++ with the vector and the queue and the map and the stack and all of those things. I think more often than not, people program in C++ as if it's C that happens to have objects, and they use the vector and they use the map. They don't use the ones from 106, they use the ones from the actual built-in STL library, but that's how most people code. Most people actually, not most people, a lot of people code procedurally and write C functions, and they happen to incidentally use the vector and the map as data structures. What I want to do is I want to write the same exact thing, support the same type of functionality in some C generics, recognizing that we don't have references and we don't have templates. We don't even have classes. So we have to do the best we can to imitate the modern functionality that's offered by C++ and Java and their templates using C that has none of it. Okay, so what I want to do is I want to slow down a little bit. I want to implement a stack class. I'm sorry, a stack data structure. I want to make it int specific, just so we have a clear idea as to how the generic should be implemented. But I'm going to just go up front and say we're going to just implement everything in terms of ints, so there's no void star business yet. Just as there is in C++, you'll normally be very aggressive about separating behavior and implementation using the .h and the .cc scheme. But if you're in pure C, you don't use .cc as an extension, you use .c, so you know that the file contains pure C code as opposed to C++ code. So what I want to write here is a stack.h file, and this is how I'm going to do it. There's several ways to do it in C, but I want to imitate the way you're used to it from C++ as much as possible. There's no class keyword in C, but there is the struct. We're going to use that. There's no const, there's no public, and there's no private. Our compiler actually supports const, but there's certainly no public and there's certainly no private. So what I want to do is I want to come as close to the definition of a class right here as possible using just C syntax. This is how you do that. Typedef, struct. The typedef keyword is required in C, it's not required in C++. And then I want to do the following. Int star elems. Int logical. Logical length. Int allocated length. And that is it. I want to call this thing a stack. Now, in the .h file, when I define the struct right there, technically all three fields are exposed, so they're implicitly public. Documentation above the .h, at least in assignment 3 when we start doing this type of stuff, it's very clear that we're just exposing these three fields for convenience so people can actually declare stacks as local variables, and the compiler knows that they're 12 bytes tall, but that you should not manipulate these three things at all. You should just rely on the functions, not methods, but functions right here to manipulate them, and just take this, except for your ability to declare the stack and that you know that it has three fields inside, Think of any struct as a black box where you just are afraid to manipulate the 12 bytes that are inside, okay? I want to write a constructor function, okay? I want to write this destructor or disposal function, and then I want to write an isEmpty function, a pop function, a push function, things like that. So here's the prototype of the first thing I'm interested in. Void star, stack, new. All I'm going to do is I'm going to pass in or expect the address of some stack that's already been allocated, okay? We were talking about the this pointer before. You know how when you call a destructor, I'm sorry, a constructor in a class, it has access to that this pointer? It's because it's passed in as like the -1th parameter or this invisible parameter before everything else. All we're doing is we're being very explicit about the fact that the address of the receiving structure is being passed in as the 0th argument. Okay, we have to because that's what cs allows us to do. I also have this function, stack dispose. I want to identify the address of the stack structure that should be disposed. This is going to be a dynamically allocated array that's not perfectly sized, so I want to keep track of how much space I have and how much of it I'm using. Okay. I also want these methods. Let's forget about the isEmpty and the depth. Let's just deal with the real functions. Void stack push. What stack am I pushing onto? The one identified by address right there. What integer is getting pressed? This one. I actually will go with it. Int right here. Stack pop. Which stack am I popping off of? The one that's identified by address right there. I just want to be concerned with those things right here. Okay? I don't know that I'm going to be able to implement very much because I only have about 9 minutes left. But I can certainly, without code, just like pictures that serves as pseudocode, just give you some sense as to how things are going to work. The allocation of a stack, when you do this, conceptually, all I want to happen is for me to get space for one of these things right here, okay? That means that this, as a picture, is going to be set aside, and you know, based on what we've talked about in the past, that it's 12 bytes that the lems field is at the bottom, and that the two integers are stacked on top of it. But as far as the declaration is concerned, it doesn't actually clear these out or zero them out like Java does. It just inherits whatever bits happen to reside in the 12 bytes that are overlaid by this new variable, okay? It's when I call stack init, oh, not init, I'm sorry, stack new, that I pass in the address of this. Why does that work and why do we know it can work? Because we identify the location of my question mark holding stack, pass it to a block of code that is going to allow, we're going to allow to actually manipulate these three fields. And I'm going to logically do the following. I'm going to take the raw space that's set up this way. I'm going to set its length to be 0. I'm going to make space for 4 elements. And I'm going to store the address of a dynamically allocated array of integers, where this question mark's all right here, and initialize the thing that way. Does that make sense? That means that that number can be used not only to store the effective depth of the stack, but it can also identify the index where I'd like to place the next integer to be pushed. That sits well with everybody? So because I'm pre-allocating space for 4 elements, that means that this as a function is going to be able to run very, very quickly for the very first calls. And it's only when I actually push a 5th element that I detect that allocated space has been saturated that I have to recover and panic a little bit and say, oh, I have to put these things somewhere else, okay? That it'll actually go and allocate another array that's twice as big and move everything over and then carry on as if the array were of length 8 instead of 4 all along, okay? You've done this very type of thing algorithmically, or at least you've seen it with the C++ implementation of templates and at least just these types of data structures from 106B and 106X, okay? I'm just doing this because I want to be able to start talking about the same implementation with ints using 107 terminology, we're going to be dealing with arrays. You can imagine that when we go generic, this is still going to be an array, just like the arrays passed to L search and B search are, but we're going to have to manually compute the insertion index to house the next push call, okay, or to accommodate the next push call, and do the same thing for pop, okay? Make sense? I do this for int I is equal to 0, I less than 5, I plus plus. I want to go ahead and I want to do a stack push. Which stack? The one at that address, and I just want to pass in I. Just draw the pictures as to how everything's updated, okay? And then right here, rather than dealing with the pop problem, which is actually not any more difficult than the push problem, I just want to go ahead and stack dispose. Ampersand of x. So from a picture standpoint, the very first iteration of this thing is going to push a 0 onto the stack. It's going to push it at that index. So I'm going to put a 0 right there and put a 1 right there. It's that 1 that more or less marks the implicit boundary between what's in use and what's not in use. Make sense? Yes, no? Okay. Next several iterations succeed in setting that to 2 after there's a 1 there. And then 3 when there's to put a 2 there. It makes this a 4, puts a 3 right there. It detects that now as the boundary between what's in use and what's not in use. You could reallocate right here if you wanted to. I wouldn't do it yet. I would only do it when you absolutely need to on the very 5th iteration of this thing, okay? So what has to happen is that on the very last iteration here, I have to do that little panic thing where I say, I don't have space for the 4, so I have to go and allocate space for everything. So I'm going to use this doubling strategy where I go set aside space for 8 elements. I copy over all the data that was already here. I free this, get this to point to this space as if it were the original figure. I allocated, forget about that smaller house. I've moved into a bigger house and I hated the older house. Okay? And then I can finally put down the 4 and make this a 5 and make this an 8. Okay? So that's the generic algorithm we're going to be following for this code right here. Okay? Now I do have a few minutes. Let me implement stack new and stack dispose, and then I'll come back and I'll deal with stack push the beginning of Monday. Let me find a board. Here's one. Actually, you know what? I lied. I can erase this. I just want to go ahead, put the .h here and have its .c profiled right to its right. I want to implement stack new to take a stack address, just like that. Recognize that s is a local variable. It has to make the assumption that it's pointing to this 12-byte figure of question marks that is that tall right there. Okay, so what I want to do is I want to go in. I want to do s arrow logical len is equal to 0. I want to do s arrow alloc len is equal to 4. And then I want to do the following. I want to do s arrow alems is equal to, this is a function you've not seen before, malloc times 4 times size of int. Now, if I tell you that this is dynamic memory allocation, you're not going to be surprised by that because the word alloc, the substring alloc, comes up in the function. This is C's earlier solution to the operator new solution. Okay, we don't have new and delete in pure C. We have this raw memory allocator called malloc. Operator new takes a count and an implicit data type because you actually say new into 4 or new double of 20. Okay, you don't do that in C. Not that we should be impressed with the idea, but the way malloc works is it expects one argument to be the raw number of bytes that you need for whatever array or whatever structure you're building. And if I want space for 4 integers, that's certainly in sync with this line where I'm saying I'm allocating 4 of them. You have to do 4 times the size of the figure. It goes and searches for a blob in the heap that's 16 bytes wide. and it returns the address of it. Okay, make sense? Okay. There is some value in actually doing this. You've seen the assert function in the assignment starter code for assignment 1. Whoops. There is this function called assert. It's actually not a function. It's actually a macro. There's this thing you can invoke called assert in the code, which takes a Boolean value. It takes something that functions as a test. It effectively becomes a no-op if this test is true. But if this is false, assert actually ends the program and tells you what line the program ended at. It tells you the line and file number of the assert, the file number containing and the line number of the assert that broke. The idea here is that you want to assert the truth of some condition or assert that some condition is being met before you carry forward, because if I don't put this here and malloc failed, it couldn't find 16 bytes, that wouldn't happen, but just assume it could, and a return null, you don't want to allow the program to run for 44 more seconds for it to crash because you dereference a null pointer somewhere. Okay, you just don't want to dereference a null pointer because it's not a legitimate pointer. It's a sentinel, meaning failure. So you don't want to dereference failure because that amounts to more failure. And then you'll get something while the program is running called a seg fault or a bus error. And I'm sure some of you have seen them. Those are things you don't want to see. You'd rather see an assert where it tells you what line number was the problem, as opposed to a seg fault, which just says, I'm a seg fault, and notice your program stopped. Okay. This will basically can be stripped out very easily so that it doesn't exist in production code. You actually don't want this failing, believe it or not, if a customer is using this code, because then it makes it clear that your code broke as opposed to their code. Okay? These can be very easily stripped out at compile time without actually changing the code. Okay? I just went over, I didn't mean to do that. So when we come back on Monday, I'll finish the rest of these 3, and then we will go generic on you. Okay? Have a great weekend.
One thing that I wanted to clarify.